Let's now learn how to plot a graph and to read values by using this experiment, the goal of which is to find the coefficient of dynamic friction between the material of that block and that surface. And remember that the coefficient of dynamic friction is equal to the friction force divided by the reaction force. And in order to measure the friction force in this case and have different values, we're testing with different masses. So the mass is our independent variable. And for each of these mass, I'm pulling this block at constant speed with a Newton meter. So the Newton meter gives me the pulling force. And since I'm pulling it at constant speed, this pulling force is equal to the friction force that's counterbalancing it. So here, this is how I managed to get these readings for the friction force. Well, now and the friction force, therefore, is my dependent variable because it's the one that I found out for each value of the mass that I set myself. So now what's the missing column here? We need to process the independent variable in such a way to have what we need to find out the coefficient of dynamic friction. And here's the missing column. So here it's the reaction force. I could have also written the weight. It's the same thing. They counterbalance each other. And in this case, we have the coefficient of dynamic friction, which is equal to the friction force, divided by the reaction, which itself is equal to the weight here. So this is how I found it. I just did W equals mg. So for example, here we have 0.5 kilograms. 0.5 times 10 is equal to 5.0. So now we have everything we need to plot a graph that will help us find the coefficient of dynamic friction. And that's the one you should have thought of graphing, friction versus reaction force. Why? Because if we graph this, we'll obtain, well, we're expecting to obtain a line because friction is proportional to reaction, and the coefficient of proportionality is the coefficient of dynamic friction. So if I graph F versus R, I should obtain a line with this equation. So then if I find the gradient of that line, I will have found the coefficient of dynamic friction. So here I drew the two axes and their scales with friction force as the vertical axis and reaction force on the horizontal axis. And now I'm going to plot each point, starting with this one. So reaction force of 5 means friction force of 1.9, so almost 2. I'm here, and I will repeat now the process for each of these 6 points. And here's what I obtained. The points are not perfectly aligned, but this is due to some lack of precision in the experiment itself and in my drawing. But basically, if I had to do what we call a line of best fit, so a line that best fits the data I have, it would look like this purple line, which has equation F is equal to mu dr. So now I'll try to find the gradient of that line. And how do I do it? I find the rise over the run. And here it seems like this point is on the line that has coordinates 10, 4, and my line goes through the origin. So the rise here is 4, the run is 10. I obtain mu d is approximately equal to 0.4. That's the coefficient of dynamic friction. Now a few warnings about the line of best fit. Imagine you obtain data like this with these 4 error bars. Well, first of all, for example, this is clearly not a good line of best fit because a line of best fit always goes through all the error bars. Then some students will maybe do like this. And if you do like that, make sure that it makes sense that the point 0, 0 is not on the line. There are many cases where the point 0, 0 is supposed to be on the line because it makes sense, and maybe it's this graph that would rather make sense. Trying to make it as smooth as possible. I didn't do a great job here. Then another case where you have these points. I see some students doing this. They think that the line of best fit is the one that goes through as many points as possible, but that's not the case. The line of best fit, in fact, minimizes the total distance between the points and the line. So here the line of best fit doesn't go through any point, but it's as close as possible to all your points. And here's about the line of best fit. I finally decided to do number 6 and number 8 at the same time because I can illustrate them with the same example. so finding the gradient of the tangent to a curve, and finding the area under the curve, which is an introduction, in fact, to differential and integral calculus and how it's applied to physics. So to illustrate this, you already studied kinematics, and if I have a velocity versus time graph, and I know that acceleration is the rate of change of velocity and velocity is the rate of change of displacement, what I claim is that with that one graph, I can actually find the acceleration or displacement at any point in time using this graph. And for that, well, let's start with acceleration, which is in fact this number 6. Imagine I want to find acceleration at time t1 here. Well, I spot the point on the VT graph at time t1, and the acceleration, in fact, is how steep my VT graph is at that point, because it's how fast the velocity is changing, right? So I draw the tangent to the curve at this point. Okay, it's the line that just goes only through this point and doesn't go through the curve. And the gradient of this tangent tells me how steep my curve is at that point. So if I do now the rise over run, the delta V versus delta T of this tangent, I find the acceleration at T1. Acceleration at T1 is this delta V over delta T that I just drew here. Now let's say I want to find the displacement at T1, and I have delta X is equal to V delta T. So I have to perform the inverse operation of finding the rate of change, because acceleration is the rate of change of velocity, and displacement is the thing for which velocity is the rate of change. And to do this, well, I go from 0 to T1, and I find the area under the curve between 0 and T1, and this area corresponds to displacement at T1. Now let's generalize a bit further. If I want to find the rate of change of any variable y versus time, I draw the tangent to the curve at the point in which I'm interested, and this, the rise over run, so the gradient of that tangent gives me the rate of change of y, which we can call g here. And then if I want to find the thing for which y is the rate of change, then I measure the area under the graph until that point t1, and we have an equation that looks like y is equal to a times delta t, where a is this thing for which y is the rate of change. And to just show you how often we use this in physics, these are a few examples. First, of differentiation. So this mathematical tool that we use in physics to find, for example, speed, we find the derivative of distance over time. Speed is the rate of change of distance over time, and you can see that we're going to do that with quite a few other things. And then these other examples are about integration. So here, these are the basics of differential and integral calculus. And when we integrate, this is when we're trying to find the area under the curve. And for example, distance is the area under the speed time curve, etc., etc. And you have a few other examples here. So now let's talk about linearizing a graph and interpreting its gradient. This is an operation you'll be using when doing a lab report. For example, imagine here if you collected data on a free-falling object, the distance it covered versus time. You know that the equation looks like something this way. S is equal to 1/2 of at squared if it's released at rest. And this is why you're not surprised to obtain a section of a parabola with this equation. And then, well, you want to find the acceleration of this object. And what you usually do is that you linearize this graph so that you can easily read the gradient and then interpret the acceleration from that. And to linearize here, we're just going to raise t to the power of 2 so that we obtain s versus t squared, and then 1/2 of a will be the gradient. So here we expect to obtain a line. This is why we call this operation linearizing. And these 5 data points will now lie on this line of best fit, for which the slope the tangent, the gradient here will be 1/2 of a. So then we can deduce the acceleration. Okay, so linearization, this is an operation that you can do when you have any kind of relationship. For example, when there's a square root relationship between y and x, knowing that y and x are the vertical and horizontal variables. So here you'll just have to raise x to the power of 1/2 and you'll be linearizing. Same here if we have a cubic relationship or an inverse relationship. You simply need to respectively cube x or take its reciprocal in order to obtain a line. So now there's a trickier one when you have an exponential relationship between y and x. Let's say y is equal to a e to the lambda x. Then to linearize, what you need to do is to take logarithms on both sides, and you obtain ln of y is equal to ln of a plus lambda x times ln of e, and ln of e is just 1. So when you graph ln of y versus x, you are supposed to obtain a line with intercept ln of a and gradient lambda. And this, by reading the intercept and the gradient, you'll therefore be able to determine these two variables a and lambda and determine the relationship between y and x.